Welcome to this Countryside COP 26 webinar. My name is David May, and you have joined my colleagues from the University of Lincoln, who are going to talk to you this afternoon about the work that we do at the university on helping to deliver net zero food. We're delighted to have you with us, and hopefully we're going to provide a thought-provoking and stimulating hour of talks and discussion. If you would like to ask a question, please put any comments in the chat and we will pick those up as we go along through this afternoon's talks. So without too much further ado, I'm going to introduce the subject and then hand over to my colleagues who are going to talk you through their presentation. So my colleagues are on screen at the moment, on probably the left-hand side of your screen, and I'll introduce them as we come to them. But before we get into their talks, I think it's important for us just to put into context why food is so important in the context of the environment and how global food production impacts the world we live in. So globally, food systems, according to the latest research published in Nature Food, account for 1/3 of global greenhouse gas emissions due to human operations and human life. That's around 18 gigatons of CO2 equivalents per year. So significant numbers that impact all of us around the planet. And agriculture is a vast industry. So we've got over 1.6 billion hectares of crop production. So that's harvested crops, that excludes land that's used for grazing. And agriculture in its broadest sense, excluding forestry, accounts for around 37% of the land that is used in the planet. So it's a very significant industry, and therefore the work we do at Lincoln has the potential for significant impacts in reducing emissions. So my colleagues are going to take you through their individual topics. So I'm going to hand over to my first colleague, Ravi, who's going to talk to you about carbon and how plants capture carbon and the benefits that can have. Over to you, Ravi.
Thank you, David. Good afternoon, everyone. My name is Ravi Valluru. I'm a crop scientist, agri-food technology. Next slide, please. So following David's global view on food production and greenhouse gas emissions issues, I will further narrow it down to the UK situation. So when you talk about greenhouse gas emissions, there are majorly 5 gases: carbon dioxide, methane, nitrous oxide, fluorinated gases, and water vapor. Among them, carbon dioxide contributes largely to GHG emissions compared to methane and nitrous oxide. Fortunately, carbon dioxide's global warming potential is much lower than other gases, for example, nitrous oxide, fluorinated gases, which means that the climate change is progressing reasonably slower compared to what we can expect if it has a high global potential. So within the UK, agriculture contributes approximately 10% to the global greenhouse gas emissions compared to other sectors, for example, transport and energy supply. However, agriculture cannot go alone. It depends on other sectors like transport and energy, which means that reducing GHG emissions from agriculture alone is not sufficient enough, and we need to consider other sectors as well to feed all of them. UK has been very successful in reducing GHG emissions in the last 30 years. For example, by 45% we have reduced, and it is expected that there will be another 40 to 42% reduction in the GHG emissions in the next 10 years. So in that sense, UK has been successful reducing GHG emissions because of its stringent policies and ambitious plans. Next slide, please. So at the University of Lincoln, crop science team focuses on several crop researches. One of my crop research focuses on carbon capture by canopy. As we know, agriculture systems are very diverse, quite diverse. We grow crops either monocropping, where we grow only one crop, or maybe double crops where we grow intercropping, or maybe we follow mixed cropping systems. So whatever the cropping system or agriculture system you take, you consider, plants by nature fundamentally depend on carbon dioxide because they absorb carbon dioxide in order to process process called photosynthesis to produce sugars, which are indeed used by the plants again to produce biomass, fruits, grains. So this basic fundamental function of plants allowed humankind to manipulate plants since decades according to our needs, including photosynthesis process. So plant scientist has been asking questions and doing research on how we can improve plants' capacity to absorb more carbon dioxide. How can we improve photosynthetic capacity? How can we improve ability to use more sugars so that they can absorb more carbon dioxide? We are partly successful in many of the research questions that we have been asking. However, we are not completely yet there because of many challenges, because plants are itself more challenging. Next slide, please. So one of the challenges is that all plants do not use carbon dioxide equally. Plants use carbon dioxide vary from plant to plant. According to all, the land plants were grouped into very broadly grouped into three different types. For example, they are called C3 plants. Most of the crops like wheat, rice, tomato, they come under this category. And they are very less efficient to use carbon dioxide and to do the photosynthesis. And 85% of the land plants belongs to C3 plants. The second group is known as C4 plants, maize, sugarcane, millets. They are very high efficient in terms of carbon usage and photosynthesis capacity, and only 5% of land plants belongs to that group. The third group belong to CAM plant types like pineapple, agave, cactus, most of the arid-related plants. And they are also very efficient in terms of using carbon dioxide and for doing photosynthesis. And 10% of the plants belong to them. Next slide, please. So following this, one of the research questions we are focusing is radiation use efficiency, which generally we as a reflection of the photosynthesis at the canopy level. It is very important trait in the crop research. How we estimate in agronomically is much more complex and less precise. So with the advent of new technologies, computer science approaches, we are using robotic platforms, phenotyping approaches, and 3D models to estimate radiation use efficiency and understand the genetic variation. What we have done recently, growing 100 synthetic derived wheat material from NIAB and the field conditions, we have used robotic technologies to generate 3D models, and we are in the process of estimating how much light can be used by each canopy, or maybe in the sense each variety, so that we know what is the genetic variation we can see, and we can identify the parents for producing new generation of material through breeding.
Thank you very
I close. Thank you, David.
Thank you very much, Ravi. That's excellent, and thank you for your contribution. And any people have questions, please put them in the chat. So I'm now going to hand over to Amir, who's going to talk to us about food production under plastic. Over to you, Amir.
Thank you, David. Well, I'm Amir Badi from School of Engineering in the University of Lincoln. I'm going to talk about sustainable food production under plastics. Well, David mentioned that food production comes with greenhouse gas emission, and my talk is really in line with that factor. First, let me start with a little bit of background. Over the last 20 years, the most dramatic expansion of the UK horticulture production has been in the area of soft fruit production, mainly strawberries, but also raspberry and blackcurrant. This expansion was driven primarily through a shift from traditional field production to advanced production systems under plastic film clad polytunnels. Well, this is mainly because polytunnels extend the growing season and protect the plants from the environmental element. On the right-hand side, you can see our research strawberry polytunnel in the University of Lincoln, our Rice home campus. Next slide, please. Well, agriculture plastic film is also a large global market, around $11 billion. And this market is growing strongly. Polytunnels are used to sustainably increase productivity and quality of both food and ornamental crops. It has driven 50% increase in UK-grown berries, well, majority of it in strawberry over past years. And it's estimated that it's going to pass £2 billion by 2021. Well, in the sustainable food cycle, probably the primary element is the production. All the farmers and growers would like to have more efficient and sustainable production system. So polytunnels support that. Polytunnels support sustainable intensification. They double production on the same area. Plastics are reused over 4 to 5 growing seasons, and mostly these plastic films are recyclable. UK production reduces carbon footprint from imported fruits as well, which is a very important factor in sustainability. Well, now I'm going to talk about 3 different projects that we have done in University of Lincoln in collaboration with other partners. Next slide, please. Well, when we talk about plastic film, each plastic film has its own optical properties, which means that we can control the light inside the polytunnels. By controlling the light, we can control photosynthesis, temperature, and pest damage. So the first project that I'm going to talk about is development of diffuse film. Diffuse films are important because diffuse lights inside the polytunnels can penetrate inside plant canopies and can enhance photosynthesis. Well, enhanced photosynthesis means better quality and more yield and fruit. They also ensure uniform light distribution over the plant canopies along the polytunnels, which also gives us uniform yield along the polytunnels, which makes yield forecasting a lot easier. The second project that we have worked on and published our data on that is the use of light spectrum blocking film to reduce pest damage. The flies that you can see in the middle column are SWD, spotted winged Drosophila or Drosophila susukii. They are probably the most damaging pest in soft fruit industry. In this project, we designed an optical rig to understand the vision system of these flies and identify the wavelength range of the light that attracts the most these flies. By cutting that wavelength range in the plastic film, we could reduce the population of these flies by 73% inside the polytunnels. Reducing population of the flies means significant reduction in pest damage and therefore significant reduction in pesticide usage, which really results in better quality foods in sustainable and more efficient way. And the final project that I'm going to talk about is development of temperature control films. The bottom picture, the map shows Almeria region in Spain. It's covered with polytunnels. Although the films, the plastic film that they are using in these polytunnels are highly transparent, but even that tiny bit of reflectance has made the temperature of this area to be slightly lower than the temperature of the neighboring area. So by designing film which can reflect near infrared light, we can control the temperature inside the polytunnels. By reducing this temperature, we need less workload to ventilate our tunnels and even less water, which is an important resource. In the next slide, which is my final slide, there are some photos of our research polytunnels in University of Reading. We are testing different materials and the plants, and they will respond to these films. Over to you, David. Thank you.
Thanks, Amir. Great talk. And I know you've got to leave us just before 4, so thank you very much. But as I say, any questions we'll pick up and I will do my best to answer on your behalf.
Thank you.
Okay, now I'm going to hand over to Marcello.
Thank you, David. Good afternoon, everybody. I'm Marcello Callisti. I work at the University of Lincoln, the Lincoln Institute for Agri-Food Technology, especially in robotics. And what we would like to do when we take decision on how to move forward with our yield, with the technology that we want to use, ideally, we would like to have the picture that we see on the right. But most of the time, what we have is just an average of the value that we would like to investigate, of the physical properties that we would like to have, and the real picture that most of the time we have is the picture on the left. So just an average of the property that we would like to analyze. what we can do to increase and detect the small variabilities and the heterogeneity that we can find in fields, in soils, in different properties inside the environment that we are analyzing, is to create different networks of sensors. But those different network of sensors, which most of the time they are static, they can analyze just at different scales. So for example, we can have a very broad scale and analyze kilometers or hundreds of meters or even small meters, but all of them, they have different scale and different temporal resolution. So they can integrate the data over 1 week, 1 month, daily in some cases, but again with a fixed amount of resolution in time and space. Most of the time, then also these networks need human intervention, both to collect the data at a certain moment or to retrieve the information in a certain amount of time or period of the year. Next slide, please. What robot can offer? Robot basically can offer 2 services mainly. Robots are most of the time mobile platforms, so they can bring and carry the sensors so that it is possible to analyze the field in different points and in different moments with a more finer scale than what you can do with traditional static sensors. Or they can navigate through the field itself, corroborating and calibrating the fixed network that you have, the fixed and static environmental sensor network that you have, patrolling around and collating the data and giving additional information with respect to the point where the static sensor are not present. Most of the time we have traditional robots which do this kind of job, like aerial drone or grounded vehicles, which are vehicles which have wheels and move around the field. When the robot carries the sensor themselves and they are not, let's say, helping a static network, what they can do, they can even adapt the resolution of the network over time, depending on the needs that we have. So, for example, if we have a huge variety in certain portion of our field, we can think of the vehicle to move closer to this high variety portion and have more data in this specific moment, and then go back when the situation change again. So we have a kind of dynamic and adaptive network. The second point, which is very important with robot, is that not only we can observe, but we can even interact with the environment. And this is partly what also we do in University of Lincoln. We have already some platforms with the one at different scales. We have drones to patrol the field from above and from the ground. And we are also developing novel machines on this kind, or totally new machine. Can we go to the next slide, please? In this case, we can see, for example, a LIAT robot. This one was used to patrol underwater and to interact with the environment accordingly to the readings or the images that we were taking. In this case, the idea was to patrol a certain area and find a specific element of disturbances, which was litter, and in this case plastic, and collect and remove. So the robot can offer also this sensor in addition to the traditional sensing only. We can have soft elements, soft arms, like the one that we saw before. We can move dexterously inside 3 branches of canopy, or we can have hybrid system like this grip. So in conclusion, robots can improve the quality of the data that we collect by varying the space of the network in time and in space, and they can interact immediately with the environment to react to the readings that we have. And that's conclude the presentation, David. Thank you.
Thank you very much, Marcello. And I'm now going to move over to Greg, who's going to talk about robotic weeding. Over to you, Greg.
Thank you, David. My name is Greg Cherniak. I'm a roboticist who is interested in applying robotic technology to agricultural applications. And the one application I'd like to talk about today about is robotic weeding. And so where is the challenge? So the current ways of producing food are reliant on a wide-scale application of herbicides, and this is to protect plants from weeds, basically. However, the use of these chemicals is not sustainable due to unprecedented pressures, and these pressures include things like the fact that wide-scale applicability of chemicals is very expensive because you have to perform these treatments frequently. In addition, if you use so much chemicals, many of these substances are harmful. So harmful to environment, biodiversity, but also to human health. And due to that fact, many of these products that are being used for spraying are being banned by the governments. So there is also an important fact that there is a growing resistance of weeds to chemicals, and which require development of new varieties of chemicals, which becomes more and more difficult process. It takes lots of years, lots of resources, lots of money, and it's a very costly procedure. So in the end, farmers are left with very few alternatives to produce food in a sustainable way. Next slide, please. So one technological solution to this problem is a robotic precision weeder. And this type of robotic technology relies on computer vision system, which is able to identify and localize crops and weeds and target individual plants. So this information can be used to simply spray less chemicals, so performing that procedure in a selective way. And this way you reduce the overall input. But you also got another possibility is to employ alternatives of killing weeds, like for example, through electric or laser zappers. But what I believe is the best way of eradicating weeds is actually a very simple and very effective way, which is basically a mechanical precision hoe, which removes the weeds by pulling them out of the soil. And such solutions already exist, like for example, RoboCrop tractor pulled systems manufactured by one of our industrial partners, Garford Farm Machinery, which are able to deploy the hose at scale. But the very exciting alternative to that, to tractors, is to deploy this mechanical precision hose on mobile robots, because these mobile robots are small, electric, lightweight, and intelligent, so they can perform autonomously day and night with very high precision. And so here on the picture, you can see an example of such a robot which is equipped with a precision hoe, and it can be deployed for weeding operations. Next slide, please. So our team at the University of Lincoln is working on vision systems that actually drive these robotic weeding machines, either pulled by tractors or by mobile robots. And this vision system enables for more precise detection of weeds that can cope with easily new crops and fields, so they are very flexible. Our vision systems can reliably discriminate between different crops and weeds so that the correct plants are identified. Then the tracking systems enable precise localization of such weeds so they can be targeted at the right location. And this information can be also used to track crops growing in rows so that you can position the entire robot and the precision hoe so that it is parallel with the rows of crop. So here on these images we can see examples of that technology. So this is what the robot, what the weeding machine sees, and you can see that the robot is able to discriminate between crops, can follow the lines, or track precise location of the objects of interest. We employ state-of-the-art machine learning techniques, which are basically based on large amounts of data collected from different crops and fields. Our main focus is actually on reducing the number of this data, which is required, since this is a costly and lengthy procedure to collect that data. Our algorithms are able to select only subset of relevant images and to learn in a way that is easy to transfer from one crop and field to another. In conclusion, we are working together with industry partners who can take this technology rapidly into the market so that the next generation of these weeding machines is equipped with these new vision systems, leading to more effective and efficient weeding operations. Thank you very much.
Thank you, Greg, for that excellent talk and fascinating subject. So can I now move on to Minnie, who's going to talk about electrification of farm vehicles. Over to you, Minnie.
Thank you very much for the introduction, David. Good afternoon, all of you. I'm Minnie Saas from the Lincoln Center for Autonomous Systems at the University of Lincoln. And my talk today will be more focused on how we can electrify future farming vehicles. We are facing the adverse effects of climate change worldwide, and statistics show that agriculture alone contributes to about 23% of the total greenhouse gas emission. There is an imminent need for transforming the current farming practices to achieve net zero. And this is why there is an increasing need for electrification of farming vehicles and the deployment of agricultural robots. These two are very closely related topics. And we benefit from the innovations or the technological advancements in the field of power electronics, machines and drives, robotics, automation, and artificial intelligence. University of Lincoln, we have a sound heritage in agri-robotics, and we are very well known both nationally and internationally for our pioneering research in agri-food. We are playing a leading role in shaping the future of net zero farming. In addition to various areas already covered by my colleagues, I would like to briefly introduce you to some of the innovative, market-led, use-driven research on electrification of agri-robots summarized in this particular slide. As we know, the electric farming vehicles, which are lightweight, these are significantly more nature-friendly than the traditional larger diesel-powered vehicles. And jointly with our industry partners, we are developing the next generation of electrically powered agri-robots. The electric or the e-hub powered agri-robots is what I'm going to present today. The electric or this e-hub drive motors that we are using for our agri-robots, these are directly built into the wheel hubs of the vehicle itself. Therefore, it doesn't have the complexities associated with the drive chain mechanisms often seen in other agri-robotic designs. More specifically, we are developing an 8 kilowatt e-hub powered vehicle for a range of field applications. And this new agri-robot offers higher torque compared to the other commonly seen agri-robots, which are often rated under 700 watts. So there is a significant increase in the power rating of the e-hubs, which means we have the added advantage of getting extra torque for operating under extreme field conditions. And of course, we can tailor the design further for achieving all-wheel drive and steering capabilities, which will help us to help the robots to traverse over the ruggedness of the field conditions. At present, we are preparing for demonstrating this vehicle later this year. And this technology enables agri-robots as well as the other farming vehicle manufacturers and their customers to benefit from the high power, high torque, greater durability, and higher efficiency offered because these are industrially driven designs. And our industry partners are also assessing the potential for automation, hoping that it would lead to volume manufacture scale up into thousands per annum. We are also aiming to fully automate this process and enhance the vehicle's autonomy or the intelligence inbuilt into the system, so that we can let the robots operate with limited human intervention and under secured or safe conditions. And this will also help to make sure that the robots are available to work under longer duration of operation, and independent of the weather conditions, they will continue to sustain the operation. Further, we are also developing our capabilities in 5G-enabled fleet management and trusted autonomy for promoting wider acceptance of agri-robots for task sharing with farmers. I would like to conclude by saying that wider adoption of electric agri-robots will be possible through close collaboration with end users, stakeholders, and across supply chain without borders. And through global partnership, I really hope that we will be able to achieve net zero food in future.
Thank you very much, Minnie.
Thank you, David.
For a very informative talk. And I'm now going to talk about another part of the supply chain for a few minutes before we go on to the panel discussion. So we've heard a lot about the farm end of agriculture, but actually we obviously have to move product from the farm to the consumer, wherever they may be. And that requires movement of goods on transport. And actually transport of food in itself has nearly 5% of the greenhouse gas emissions within the food supply chain. And in particular, the area that I'm looking at, which is refrigerated goods, has a significant impact to that. So refrigerated goods, whether that's chilled or frozen, add at least 16% more to the emissions compared to non-refrigerated goods. And actually some estimates put that as high as 40%. And much of that is within the urban areas, so the areas that are around people's homes in cities. And we know 81% of the transport is on road as opposed to air or sea freight, and that has a significant impact on the local urban area from, in the case of chilled food, from the diesel units that are often powered at the front of the trucks to keep the products cold. And they produce not only CO2 or greenhouse gas emissions, but also we have high levels of NOx and particulates. So we've been working on a project which is part of the Clean Air Project on looking how we can remove those emissions completely from the urban environments. So the project has been a collaboration with a company called Hubble Logistics, and it's been to remove the need completely for having diesel engines for chilled goods in urban areas. And so by moving products in what is a very large cold box, but using phase change materials which allow the products to be maintained cold. So effectively that acts like a giant battery. So we're storing the energy which can be used, green energy that can be used and to keep the pods cold. We are currently have developed an insulated box with the phase change material in it, and we're currently on trials, and these look to be able to maintain products at the right temperatures for somewhere in the region of 13, 16 hours and potentially longer depending on the ambient temperatures. So by being able to move food without the need for diesel refrigeration units, we have the potential to remove those emissions from urban areas, and also we can lightweight the vehicles, so we can remove the need for heavy chiller units, which also has significant benefits as well as removing the diesel that is used to power those. So as we've said, most of that emissions goes on in urban areas on the last mile of the delivery, and that's increasing as more consumers want their food delivered to their doorstep as opposed to them going to the supermarket. And part of this work has been to do a life cycle analysis of the system, and we've identified that most of the emissions come from the the actual movement of goods rather than from actually building the infrastructure. And on our initial calculations based on the design that we've come up with, suggests that we can reduce NOx pollution by around 20% and particulates by around 31% in absolute terms, but also around 26% for CO2 equivalents. So by changing and rethinking our supply chain, we can potentially significantly reduce the amount of emissions that come in moving the food from the manufacturer, from the farm to the consumer. It's also worth noting that something around 28% of all vehicle movements are with empty vehicles. And these sorts of systems are part of the solution to allowing us to be able to mix both refrigerated and non-refrigerated goods. And so again, by improving the efficiency of distribution, we have the potential to reduce the amount of pollution per ton kilometre of goods moved. So really interesting area of work, somewhat different to my colleagues, but hopefully you found that interesting. And if you'd like to hear more about the work that the University of Lincoln is doing, please come and join us at the FPC Futures event on the 4th of November, when you can hear talks around the subjects today, but also many others on how agricultural technology is developing within the food industry. First, so I'd like to thank all our speakers, and then if you want to get in touch, please do get in touch with us, email us. We're now going to move over to the panel discussion. So if I can have my colleagues back, and I will stop sharing my slides. And then I'm going to start off. We'll have about 15 minutes of panel discussions, and then I will come to the questions in the chat. So if anybody's would like to ask some more questions, please do post your questions for us. So I'm going to open up with some sort of quite general questions, and then we'll perhaps drill down into some more specifics as we go. So perhaps each of you could comment on where you see the main barriers to adoption of the technologies you're working on, and specifically why robotics, for those working on robotics, has been slower to take off in agriculture. I'm going to start off with, I think we'll go to Minnie first, and then I'll come to Greg next after that.
Thank you very much, David, and all the speakers for the insightful talk. With regards to agri-robotics, we are in a phase where we are able to convince farmers, growers, and businesses about the benefits of agri-robots for numerous applications. And the main, I would say, the technology-wise, there has been a significant leap in the areas of the machine design or the platform design, AI, autonomy, perception, navigation. There are various advancements in this field. But the main limitation, or when it comes to uptake by the end users, is because the overall capability of an agri-robot today is not adequate compared to what they can still achieve with a larger a traditional vehicle. So that is a limiting factor. So we are in the process of enhancing or improving the performance of agri-robots in various ways, very much like what Greg was mentioning us. They are really good at weeding application, and they are proving very efficient for harvesting of soft fruit. So there are numerous strands of agriculture where they are outperforming the traditional vehicles, but it is about time and advancing the technology, and about creating a better understanding for the community about the benefits, the added values of agri-robots.
Thanks, Minnie. Greg, perhaps you could pick that up and see how you see fleets maybe of mini robots taking over.
Yeah, so I think potential with or benefits of robotic technology include the fact that these are small, lightweight robots that do not cause compaction. They don't require such a large infrastructure as for example, big machines and tractors. But at the same time, they are smaller. So to do the same amount of work, you need more of these robots. Yeah. So I would say one of the barriers that it's very trivial one is the price of individual robots. Yeah. This is still quite expensive technology, maybe because these robots are not produced in mass scale, like cars, for example. So price is still an issue. And for example, if you take the sensors, which are used for navigation and for safety, often these sensors basically cover half of the cost of the robot. Yeah, and so that's how to say, the progress in technology has to address that issue, how to make these machines more affordable.
Okay.
And the second one is safety. And safety is because these robots are meant to work autonomously. So we are not yet at the moment where we can guarantee, where we can trust our AI systems for to leave the robots, for example, to work for a week without any supervision. Yeah. So I would say these are two main barriers.
Okay. Brilliant. Thanks, Greg. Marcello, in your field, where do you see the barriers?
Well, I think that one of the main problems that we have to address is that we have to interact with the farmers, okay? Because sometimes when we develop the tools as the engineers, we are in love with what we develop, but maybe an interaction with the farmers will give us a better understanding of where to focus and when to provide real advantages. So in my cases, what we want to offer is something that does not exist now. It's not only an improvement. And for hitting this point, and this is true also in other fields, not only in agriculture, what we should do is to interact with the farmers and find a not spot where the robot do something that the other vehicles cannot do. For example, in the intercrop that Ravi was showing, traditional vehicle maybe can struggle because there are a lot of varieties, not simple, it's not well structured. And in this case, this can be the perfect environment for robots that can sense and can go around with no traditional actuation methodologies. But still the barriers are very high because the technology requires skills and understanding of the technical side, which is not shared among all the curricula right now.
Thanks, Marcello. Ravi, do you want to just pick up on, because obviously you're working perhaps pre the regular farmer, the breeder end, where do you see the barriers and the opportunities for the breeders and using technology?
Yeah, I think so. When you consider farmer versus breeder, definitely breeder will be much more interested to use the technological innovations in order to progress what he is doing, especially because they deal with thousands of new lines. When you make a new cross, they produce thousands of lines, and it is necessary for them to understand which of this line among these 1,000 lines perform better so that they can take it forward. In that sense, they are very much interested to bring the advanced technologies to screen the germplasm compared to farmers. However, from that side, they are more happy to invest a lot of money for getting it, but which is not the case for the farmers. So they will see cost as one of the major barrier, and then skills, how much skills they need in order to use this technology to get a meaningful output from out of it using the technology that can be useful to implement in the field conditions. So I think the requirements and barriers could be slightly different when you consider farmer versus breeder.
Thanks, Ravi. You've touched on a really interesting point about skills and the changing skills that the industry needs. Perhaps if I can open it up to Marcello, what skills do you think we're going to need, and where do they sit? Will they be with the farmer, or will they be with the roboticist or the scientist sitting in an office, perhaps remotely looking at their crops? And how do we get more people to realize actually this is perhaps the most important industry in the world, because we all need to eat?
Yeah, it's a very interesting question, and indeed it's very demanding question right now for young people, because actually what we want to have is not, let's say, polarized and very specialized curricula right now. So the skills that we need in this moment are a kind of transactional skill. So exactly when we talk about agri-robotics, we are mentioning two different curricula. And this is not common. Sometimes we have just an agricultural curricula and then a robotics one. The merging between the two and knowing both, let's say, something of both the domain is the key that we need in the future, I think. So basically, if I have to summarize with one skill, is openness to be receptive in different domains and be able to not work only in your own specialization, but you're open to multidisciplinary curricula. That's the more important skill that you need, this openness of mind to work in different aspects.
Really interesting point. Yes. How do we have an open mind to new technology? Minnie, I know you want to come on because you're passionate about this subject. So perhaps do you want to have a couple of minutes to expand?
I would like to add to what Marcello just said, because if you look at the agri-food industry, there is a huge shortage of skilled people. By skills, what I mean is what we need is translational hands-on skills. So when it comes to training the next generation of engineers or crop scientists, it's important to make sure that they can take their knowledge and apply it to a very important industry. Because if you look at me, I'm a space engineer, but I love working in the field of agri-robotics, and I'm applying my skills from the field of robotics for space applications or space missions to agricultural applications. So there should be a easy way to navigate between cross-sectional or cross-sectorial applications, and developing translational skills for the next generation of workers is really key. And within the University of Lincoln, we are having several programs that really promotes and attracts more and more youngsters to specialize in agricultural science and agricultural robotic engineering. And we are one of the largest centers leading in the EPSRC funded the Center for Doctoral Training, which trains next generation of robotic engineers and scientists. So I think there are a number of programs that we are offering to attract the next generation of youngsters to take agri-food or agri-robotics as a career in future.
Thanks, Vinny. I'm going to come to Greg and then Ravi to wrap up this question. Greg.
Yeah, I think my colleagues probably addressed the most critical aspects of this skill set. I would say, one, until we've got these programs that cover actually both aspects of the application, like agriculture and technology, I think there has to be this openness, and people like myself, roboticists, we have to get additional training in application itself, understand the basis of agriculture, crop rotation, crop protection, all that stuff. I think ourselves, we have to learn that so that we can also pass this knowledge to our students. It's inherent. You cannot separate these two things. You cannot always work with someone else who's got the agricultural expertise and believe that this can work. Yeah, so you have to also be open. And the same comes with the farmers. We have to remember that farmers are actually very very well accustomed with technology, but it's maybe the technology and skill set that they haven't been exposed to when I think about robotics, for example, because there is lots about computer science or programming skills, understanding machine learning, how we can use the data. So it's a completely new set of skills that are required to be comfortable around the future technology. Yeah. So yeah.
Thanks, Greg. I think if technology, which I'm sure will lead the next agricultural revolution, then we're going to need a very wide range of mix. But coming back to the plants, and Ravi as a plant scientist, have we got the skills to meet some of these challenges? And how can we make sure that the technology supports and assists us to deliver some of the objectives that you've laid out in terms of having plants which are better at sequestering carbon, produce more yield per unit of input and resource?
Yeah, so in that sense, I think I agree with colleagues that what they have already raised, multidisciplinarity. Traditionally, it is very common that every discipline comes with their own discipline, with a little bit of exposure to outside allied sector, associated sectors. So in that sense, most of the agriculture students comes with most of the agriculture knowledge, while the less knowledge on any other non-agriculture subjects. So once we have the knowledge coming from the multidisciplinarity, which is necessary, in most of the cases where when you're dealing with a subject, for example, crop science, now we want to have a computer science, it is difficult to get experience and knowledge in both disciplines because they don't go together, but there is to some extent where you can capture them and putting them together. So that is a process. For example, program highlighted by Mini, CDT program highlighting that bringing the computer science versus the crop science together knowledge. So if you can be able to give to some extent some knowledge on these disciplines, that person can be able to come up with the new ideas so that he knows what he's doing, how he can do it, and further collaborate with the pure experts so that he can deliver something meaningful from the research point of view. But from the farmer's point of view, it's not necessarily that they need to know each and everything, but they can come up with the ideas. A group of farmers or maybe villages or maybe regions, they come up with the systems where they can use the technology in a more useful way.
Okay, thanks, Ravi. I'm going to try and pick up some of the comments and questions in the chat. So the first one is for you, Ravi, which is, to what extent does improving canopy carbon dioxide capture solve climate change issues?
Well, I think improving the canopy carbon dioxide capture will solve to some extent climate change issues, although it's not the only activity that can reduce all the climate change issues. For example, that we know in the science, there are 400,000 different plant species around the globe. And every year we are discovering 2,000 new plant species. And altogether, taking the forest, only considering the forest around the globe, it is estimated that approximately 7.5 billion metric CO2 is captured by the plants per year basis. So if you are still sitting here today and talking about the climate change, which means that we are producing more carbon dioxide than what plants can absorb globally on a year basis. So even improving the carbon dioxide captured from the canopies, it will not still solve it, but it can largely reduce the climate change effect. It will really reduce the speed of the climate change progression over a period of time. But I think it is all coming through as a cumulative effect.
Okay. Do you see there need to be a shift maybe in people's dietary choices to those plants which are better at capturing carbon, or is that perhaps a step too far?
I think that is one option where people have been highlighting moving towards, for example, plant-based protein. We are getting more proteins from the plants. But I think that may be very, very difficult challenge for the people because, around the world, there are thousands of different ethnicities and different preferences people have. It is asking one of the group, for example, stopping the preference that they have been living with for the years, decades. Take rice, for example. Most of the Asian countries, including myself, depend on rice, and which we already know that rice production, which is a standing water, produces a significant amount of methane over one cycle. So if you ask all the Asians stop not eating the rice so that you can reduce the methane production, which is contributing to greenhouse gases, that is going to be almost impossible. We cannot really stop it. But having some of the systems, how you can manipulate the system, the way that you grow rice cultivation, for example, rather than standing water, come to rainfed situations where you don't give the standing water, whether it will reduce the methane production from the rice fields, that would probably have some impact, how you can reduce some of the greenhouse gas emissions. But I think we cannot really change the cultural preferences of what the people have been living with.
Okay, thanks, Ravi. I'm now going to go on to the next question from Marie. So, how can we scale up deployments of small robot weeders to large fields so they can compete with the heavy tractor-pulled machinery?
Thank you for that question. In a sense, I think I've partially answered that when we were talking about the main barriers. Yeah. So which was the price and the safety. What I would add maybe here is this thing that looks quite mundane and not very interesting, but it's actually all the auxiliary things that you need to have to actually have a fleet of robots operating on your farm. So it's the entire infrastructure. So where do you store the robots? How do you charge them? How do you service them? How you communicate with these individuals? That requires completely new infrastructure, and many of the existing farm environments are not yet suitable for different reasons. For example, I don't know, the mobile signal reception in many farms is still quite poor. So and lots of that communication technology in robotics would rely on very reliable mobile network. So there is lots of infrastructure that it's still not there, that would have to be deployed, so that then there are clear advantages and benefits of deploying these smaller robots, and infrastructure that will enable these small robots to basically compete with the large tractors.
Okay, so thanks, Greg, and that actually neatly leads me into Mini, because if we're going to electrify all of our vehicles, have we got the infrastructure to do that in a lot of these rural areas?
I fully echo what Greg said. So infrastructure is indeed, one of the biggest requirement. Although one can say that at present agri-robots are smaller, but the whole focus of electrification is to really develop larger or medium to large scale agri-robots with greater capacity, which can, which would in one way or the other will be comparable to these larger tractors. So the aim is not to build large vehicles, but small to medium scale or medium to large scale, which offers such capacity. Now, infrastructure is something also linked with the requirement for IoT enabled or interconnected robots. So when we talk about deploying multiple robots, it's important to have such infrastructures which are more connected with having the appropriate signals, communication signals. So everything is, in a sense, then driven by the Agri 4.0, which depends heavily on all these advancements in the field of communications. So it's not just about the size or the spec of the robot, but there are various other additional transformation needed for wider adoption of agri-robots.
Okay, thanks, Mini. We're getting close to time, so I'm just going to ask Marcello and then Ravi just have one more comment, and then I will wrap up. So if we can be brief. So Marcello, is it the wheel or is it a walking robot, as you showed earlier?
I think that the very long feature will be legs. That's my impression. I mean, legs in a certain sense make us agility to move in very structured terrains, to reduce the compactness of the soil, to be more agile between crops. So legs is a clear direction that mobility in a structured environment can be the solution, but still we are very, very far technologically under the energy consumption. So for now, the answer is still the wheels in a better way, as my colleagues said. So short term and medium terms, I think better wheeled vehicle, maybe long futuristic terms, let's say some legged robots in the field.
Okay.
So that's the answer for me.
Thank you, Marcello. Ravi, I've got to leave a plant scientist to have the last word as a plant scientist and agronomist. So what do you think, where next for plant research, and how will it help reduce the impact of climate change of our food systems?
Oh, I think that would be a difficult question to say there is only a particular activity that we can rely on. There may be some other activities on the plant research where it could contribute. For example, there are already some programs running in different parts of the world working at how much carbon fixed by the plant can be stored in the roots, for example. So they have been working on such projects and improving that one, because we know that there are some feed forward effects within the plant and it's not able to manage everything carbon that it captures. So the question is, can we improve how much carbon is transferred to the root so that we can store more carbon in the soil that is contributing to soil organic pool, and that will not affect anything. And there are some lichens as well, which research has been initiated. So I think in addition to carbon captured by the plant, which are directly exposed to the environment, and there are also some other activities like roots, which are not exposed to the environment, could be useful also. And there are research already ongoing.
Okay, thank you very much, Ravi. Thank you very much to all of my colleagues for your contributions today. I think we've slightly overrun our time. Hopefully, those of you who've been listening in or watch this on YouTube at a later date have found our talks interesting. If you'd like to get in touch, please come back to us, and hopefully we will see some of you at our event in November. So thank you very much, everybody.
Thank you. Bye.
Thank you all. Bye.
Thank you.